Gaussian curvature. In other words, a two-dimensional surface embedded in three-dimensional space. So let's take this page, which is numbered 1 to 9. On page 1, ds squared, grr, which is a function of r dr squared plus r squared d theta squared. There's only two dimensions here, r and theta. That's what we're giving the coordinates on the surface. Okay? Gr with 1 is the square root of grr. G theta, which is the square root of g theta theta, is simply r instead of r squared. Okay, what's the Gaussian curvature? There's only one curvature because there's two dimensions, r and theta. There's only r theta. That's the only curvature that there is. Okay? What is g theta with 1 theta? It's only r. What's the derivative of that with respect to r? It's 1. Okay, that's what I wrote over here. What is gr with respect to theta? It's 0. You have this Gaussian formula. All right, let's do that computation. The regular bracket one is simply 1 over those two things, which is 1 over square root of grr, 1 over r. Okay? In the curly brackets, what is g theta comma r? Well, what's g theta?
R.
Is r. What's the derivative with respect to r? 1. Divided by gr. Okay, so it's 1 over gr. Then the derivative of that with respect to r.
Squared g. We don't know. Do we know if
We don't know. We don't know what it is.
Function of r.
Yeah, gr is a function of r, but we don't know what function it is.
Right. Okay.
So
So
it's
it's just the derivative.
Just the derivative of that. A to theta, a to r. Both of those are the same sign, right? So it's plus 1. Then you have gr comma theta. What's gr? It's square root of grr. It's a function of r. Is there a derivative with respect to theta? No. So that whole piece vanishes. So you just have that first piece. So I wrote it down as kr theta equals, first you have the square bracket piece, which is r gr to the minus 1, times what we said before, 1 over gr, derivative with respect to r. Okay? So we plugged in, for the Gaussian formula, this particular metric. Now, not every two-dimensional surface will have this metric. It'll have only 2 pieces in the metric. If you choose your coordinates wisely, you don't need more than 2, right? So it'll have, let's say, something like that. Depends on whatever, how many coordinates and how you're going to choose it. But let's say you can have this kind of system with 2 coordinates. Okay. Sometimes I'm putting prime, sometimes I'm putting that little comma with respect to r.
All right. I got it.
And sometimes you may notice in the notes, when there's a derivative of a function of time, often I'll just write prime and I mean dot, because I'm taking the derivative with respect to the parameter that it's a function of. Okay, so it's sloppy notation, but it's usually quite understood exactly what I'm doing. I just rewrote it using a certain identity. I was just doing a little calculation, whatever, and plugging in, instead of keeping it in terms of the GRs with one R, I put it into terms of GRR, which is its square, the one that actually appears in the metric.
Like
Okay?
just a regular
This is
mathematical
just a
identity?
little mathematical thing that I,
It's
you know.
not like a GR.
No,
identity.
nothing. It's just something I calculated, whatever, it works. So you end up that you can write the curvature is equal to the bottom line of that piece, square brackets minus 1 over 2r times GRR inverse prime. So that's written in terms of GRR rather than GR. I mean, you can do that at home to see that, in fact, it was that when I did that little identity. Okay, so that's simply a Gaussian curvature computation for this metric. Just plug it into this. Okay. The bottom thing I did using Gauss's notation, forget about that. Let's say I suppose that the curvature is constant. In other words, we have this two-dimensional surface, and it's this metric, as we wrote over here, but I'm telling you that the curvature is constant. It's a surface of constant curvature, for example, like a sphere. Okay. What does that mean? That will mean that the curvature that we calculated will have to be constant, be the same constant. It's constant everywhere, the same constant everywhere. On the top of the second page, kr theta, which we just computed, we're going to say it's equal to little k. It's a constant. Now go through the next few steps yourself. If indeed kr theta, which is that, is equal to k, what does that tell us about grr? This is important, so go through the next 3 lines yourself.
Why did you integrate it?
I wanted to find out what grr is. I'm solving for grr.
If it's 1 over GRR, shouldn't it be?
There's a prime.
There's
Oh,
a
is that
prime after the
prime?
minus 1. Yeah, I'm sorry, it's such tiny little letters, it's hard to see, but
Oh, is that's what that is? Okay.
Yeah. okay, do you all follow? You see that? The GR is 1 over b minus kr squared. It's just a simple equation. What happens when k is 0? In other words, a surface of 0 curvature. What is a surface of 0 curvature? A flat thing. What happens? K is 0. So now we can write the metric. The metric that we wrote in the beginning as just GRR plus r squared d theta squared, we now know what GRR is for this specific case of constant curvature. It's 1 minus kr squared to the minus 1. Okay? It's worth taking a minute to go through yourself now to convince yourself, because we'll see this a lot. It's very important. These 2 pieces that we just covered, okay? The upper part of the left-hand side and the upper part of the right-hand side, including that little identity. Shouldn't take you more than a minute and a half to go through it. There's no substitute really for just seeing it yourself and being convinced.
So the one on the left is more general, right? And the one on the
Right,
right
the one on the left exactly is for a specific type of metric where we're using coordinates r and theta, and where the r square has only a function which is a coefficient, which is a function of r. There's no function of theta in there, and the other one. So in other words, it's a spherically symmetric situation where we're using spherical polar coordinates, right? But we didn't necessarily specify that it was what kind of curvature it has. The one on the right is saying, okay, you found it out for that kind of. It's not exactly totally general because I'm limiting to a certain type of coordinate system and so on. For that coordinate system in that situation, this is what you get. Now I'm telling you that it's constant, so I set the curvatures that you found constant.